find the normalized eigenfunctions of the boundary value problem. So first we find eigenfunctions, then we'll normalize. Okay, to find the eigenfunctions we need to consider three cases, because this lambda, which is a real number, could be positive, negative, or zero. So let's say first case, let lambda be positive. Okay, to simplify our work, we can let lambda be mu square, where mu is positive. Then this ODE can be written as y double prime plus mu square y equals 0. And to solve this, we find the characteristic equation, which is r squared plus mu square equals 0. Then we solve for r, that is, it will be mu I plus minus. That means cosine mu t and sine mu t are two solutions, and we can write down the general solution, that is y as a function of t equals c1 cosine mu t, or we can go for mu x as well, okay, plus c2 sine mu t. Note that mu is strictly positive. Now we apply these two boundary conditions and determine c1 and c2. To apply these boundary conditions, we need to determine prime, that means derivative. Then derivative of this function is, cosine is negative sine, so mu c1 sine mu t plus mu c2 cosine mu t. Okay, using first boundary condition, that is y prime at 0 equals 0, we get y prime 0, that's here y prime 0 is 0 when t is 0, so we get negative mu c1 sine 0. Sine 0 is 0, so whole thing is 0, 0 plus mu c2 cosine 0, and cosine 0 is 1 times 1, don't have to write, and mu is strictly positive. We got mu c2 equals 0, and mu is strictly bigger than 0, that forces c to be 0. Okay, now we can go back and update our solution, because c2 is 0, so we don't have this term anymore. Also, to apply the second boundary condition, now we can y prime here, we can get rid of this term because c2 is 0. Using the second boundary condition, which is y prime at 1 equals 0, so we are using here, okay, y prime here, so y prime at 1 when t equals 1, so y prime is 0 equals negative mu c1 sine 0, sorry, t is 1, so sine mu, okay, it's not 0 because t is 1, sine mu, and mu is strictly positive, so sine mu may or may not be 0. Okay, so in this case, this forces mu is not 0, obviously mu is positive, and c1 does not have to be 0 because sine mu can be 0 at places. If we graph y equals sine x, then it becomes 0 at a lot of places, okay, where mu is positive. So this let c1 not equal to 0, then that forces sine mu to be 0, and we know that sine mu is 0 when mu is integer pi, n pi, like 0 degree, but sine is mu is positive, so 180, that's pi, back to 2 pi, 3 pi, etc. This means mu is integer pi n pi, where n is bigger than equal to 1, 1 2 3 4 5. Okay, mu equals 0 is sign mu is 0 when mu is 0 as well, but mu is positive in our case, so just 1 pi, 2 pi, 3 pi, etc. Okay, so we got lambda positive be an eigenvalue, but we got infinitely many, and lambda is in fact mu squared, so we can write down eigenvalues are in this case positive lambda, and lambda is mu squared, mu is n pi, so n is squared, pi is squared, where n is 1 2 3 etc. And eigenfunctions in fact, that's the solution, are given from this. Okay, solution is y. C1 is arbitrary constant, we can get rid of that, so cosine mu t, where mu is n pi, so cosine n pi t, cosine n pi t, where n is 1 2 3 etc. Okay, we need to normalize them, so let's see if we have any more eigenvalues and eigenfunctions. Okay, so we consider the case lambda positive. Next, let's consider lambda 0. So the case let lambda be 0, then the ODE is just y double prime plus lambda y 0, lambda is 0, so it's 0. If we integrate one time, then we get just a constant, so y prime. Integrate one more time, so we get yt equals a t plus b. So this is the solution. And if we go back here, y prime 0 is 0, y prime at 1 is 0, so we use these two boundary conditions to determine a and b. So using y prime 0 equals 0, that means here, so y prime is 0 when t is 0, but there is no t, so a is 0. Okay, and if we go to the solution now, a is 0 means we get rid of this. Let's use the second boundary condition, which is y prime at 1 equals 0. So y prime means we need to use this again. So y prime is 0 when t is 1, and there is no t, so a equals 0. So in both cases we got a equals 0. That means, look at the solution here. So y is b arbitrary constant, then we can take y equals just 1. That means lambda equals 0 is an eigenvalue with the corresponding eigenfunction just 1. We can write b, but b is arbitrary constant. Thus we can write lambda equals 0. So let me write this way. So lambda equals 0 is an eigenvalue, and the function y equals 1 is the corresponding eigenfunction. And in fact there is 1, so it's already normalized. Okay, we don't have to normalize anymore. So I'll come back for normalization. Now the third case is let lambda negative, and we can say we can take lambda negative means negative mu square and mu positive. Okay, in this case the given ordinary differential equation y double prime plus lambda y becomes y double prime plus lambda is minus mu square y equals 0. Now we solve this. We take characteristic equation, which is r squared minus mu squared 0. That means r equals just plus minus mu. Whenever we have plus minus not I, then we get hyperbolic cosine hyperbolic mu t sine hyperbolic mu t are two solutions. We can work with exponential functions, but these are better. So yt solution c1 cos mu t plus c2 sine hyperbolic sinh mu t is the solution. Now we use the boundary conditions and to determine c1 and c2. Okay, to use the boundary condition we need to find its derivative, and for hyperbolic functions we never get negatives. So derivative of cosine hyperbolic is sine hyperbolic mu outside sine hyperbolic mu t plus mu c2 cosine hyperbolic mu t. Using y prime 0 equals 0. So y prime is 0 when t is 0. So we get mu c1 sine hyperbolic 0, which is 0, plus mu c2 cosine hyperbolic 0 is 1. Okay, and mu is positive in our case. Okay, because negative mu squared, that's the negative number. So that forces c to be 0. C2 0. Now we can update the solution. C2 is 0, so we don't have this anymore. To apply the second boundary condition, we can also update that part. This is not there anymore. Now using y prime at 1 equals 0, that's the second boundary condition. We get here, no here, okay, we apply here. So y prime is 0 when t is 1. So mu c1 sine hyperbolic mu, so this mu. Okay, and mu is positive. Okay, c can be positive, or I mean we try to avoid c1 being positive. Let's see, sine hyperbolic mu is positive number. Okay, and this sine hyperbolic is 0 at only one place, where when mu is 0. Okay, sine hyperbolic x is 0 if and only if x is 0. But in this case mu is positive number, so this is never 0. This is never 0. Mu is never 0 because it's positive. That means c1 must be 0. Okay, so we have c1 0 because sine hyperbolic positive is never 0. This is never 0. Mu is positive. Now we got c1 0. That means if we go back here, c1 is also gone. So we got solution as yt equals 0. Okay, that means lambda negative is not an eigenvalue. Okay, thus we got two. Thus the eigenpairs in the first, when we have lambda positive, we got n square pi square cosine n pi t, n square pi square eigenvalue, and cosine n pi t eigenfunctions. Okay, and 1 2 3 etc. And we also saw lambda equals 0 eigenvalue, and 1 is the corresponding eigenfunction, and 0 1. And the question is, we need to normalize. So 1 means it's already normalized, we don't have to do anything, but these eigenfunctions are solutions, so we need to normalize now. Okay, normalize the eigenfunctions. To normalize, we use the condition. Now we take this integral 0 to 1, so we multiply by some constant kn and we determine that. So kn times cosine n pi t, we take a square, and there's a weight function r, but that's 1 in our case, and we take that to be 1. So we multiply these eigenfunctions by some constants so that this definite integral is true. So let's find that. Okay, now the case is find kn's. So this one kn is squared, so we can pull outside. Kn is squared, that leaves 0 to 1. Cosine is squared. Then how do we integrate cosine is squared? Cosine is squared is 1/2 1 minus cosine 2 theta double angle. So 2 n pi t equals 1. Kn squared, 1/2 can be pulled outside, out 2. Now let's integrate. Antiderivative 1 is just t minus antiderivative of cosine is sine 2 n pi t. We divide by 2 n pi. Now we go from 0 to 1, and we want this to be 1. Okay, so let's plug in upper limit, lower limit. So we got kn squared over 2 outside, t equals 1, so this is 1 minus, plug in 1 here, t equals 1, we get sine 2 n pi. I mean, n is integer, double integer pi, and sine integer pi is 0, by the way. Okay, it's the 2 times, but it's still 4 pi, 6 pi, etc. 0. That's from 1 minus lower limit. Let's plug in 0. So this is 0 minus sine 0 is 0. Okay, so from inside we got just 1. I mean, there is no contribution, 1. So kn squared over 2 equals 1. And that implies kn squared equals 2. Okay, and kn square root of 2. And we don't consider negatives as positive too. So the normalized eigenfunctions are, we just multiply this by root 2. So thus the normalized eigenfunctions root 2 cosine n pi t, and we have, when lambda equals 0, we got 1 as well, so 1, and where n is 1 2 3 etc.